email that I sent out before break that explained what was going to be in the test?
Yes.
Then go look at your email. It's going to cover, guys. Can you close that door? It's going to cover graphing of velocity and acceleration and distance. It's going to cover all of the motion for constant acceleration and constant velocity. Okay? It's going to cover all of that. What it's not going to have, I'm not going to ask you a question of the intersection piece, right? Where two things collide. Okay, like I've got the thing jumping off the cliff and it's got to get into the cart. If the cart's moving at a certain speed, let's catch it, right? But keep in mind that problem is essentially all the stuff you've done, right? The only addition to the intersection problem, the only addition the intersection problem does on top of your current problem, on top of the stuff you need to know, is just talking about the time connection, right? Solving time from one to use it in the other. That's all. That's the only thing I'm not going to ask you about, right? And that's the next step. But it's the same thing. It's just that one piece. Does everyone get that? That you still need to know how to do those problems. I'm just not going to ask you the time connector, right? So, for example, okay, if I've got a cliff, right? And I have, here's my example from this morning. I have Superman, okay? All right, and he is about to, I'm sorry? I'm about to, give me a second. I'm getting his cape. Yeah, he's Superman. The problem is Superman just saw some kryptonite, okay? Superman had some kryptonite, okay? And he's going to jump off, but he doesn't know it. So he's going to do what? He's going to fall straight down. So he's going to jump off horizontally, okay? Which means he's going to, and we're going to ignore the horizontal for the moment, okay?
Question.
Yes, sir.
So say like he steps off.
Yes.
Typically be jumping horizontally first.
Yeah.
At a very, very slow rate.
Yeah, I mean, if you're moving forward, you have a forward velocity, right? You can move, let's say you're going to jump off of a cliff. Let's say you're going to jump off of a cliff to land in the lake. At some point in your life, you either have done it or you might do it where you jump off of like a tall like rock to jump into a lake, okay? You might have to clear things below you. Mm-hmm. You may not, right? It may be a rock that juts out. Well, you may have to take a step, okay? And it may clear like the 2 inches of rock at the bottom, right? Because when you take that step, you're still moving forward, okay? But you won't be moving forward as fast as you would be if you ran to jump, right? And you know if the rock is really jetting out below you, you really have to run to clear it because you need to be horizontally at the position for the rock. You need to be here, not here, by the time you land there. Does that make sense? Right, by the time you fall this distance, you need to be here. And that, success or failure, right, depends on your initial horizontal velocity, okay? So even if you step, you have a small amount of horizontal velocity. If you had none, you would just sort of scrape along the wall.
Okay.
You follow me? Okay. All right. So Superman's going to step off. He thinks he's going to fly, but he's not. But Superman does have this little cushion down below, okay? All right, that he's going to hit. So he will be safe, okay? His height is, let's say, 80 meters above the height of the cushion, okay? What I'd like you to tell me, number one, is the time it's going to take for him to land on that mattress. So what is the delta time to land on the mattress? That's problem number one. Okay. Problem number two. Problem number two is this. Okay. It is Superman has regained his powers, okay? and there is a bomb. Did you say casually?
Yeah.
It's casually, there's sort of a bomb here. Okay. And obviously the bomb has a fuse, and the fuse is lit. Right? Okay. Wouldn't be a bomb without a proper fuse. Okay. And
Oh, it's already lit.
it's already lit. Okay. Time is of the essence. So Superman is here. Okay. Yes, he's pushing the bomb away. He's trying to push the bomb to safety. Okay. Did you say good luck? Yeah. And he's got to go 2,000 meters
Holy crap.
to get to safety.
I just said screw it.
Okay. The initial velocity of Superman is 0 meters per second horizontally. Okay. His acceleration horizontally, the acceleration in the x direction, is plus 5 meters per second squared. The question is twofold. One, what's his time to get to safety? And what's his final velocity? Where are you at? Yeah, acceleration in the horizontal position, direction, excuse me. So acceleration in the horizontal direction, 5 meters per second squared. What is the time it's going to take him to get to safety of 2,000 meters? And what's his final velocity? Because he's constantly accelerating at that rate. He's constantly accelerating horizontally at that rate, starting from 0.
Velocity initial
Is 0. How is this problem fundamentally any different than the other problem?
Is there gravity?
Well, there's always gravity, but from the math that we're dealing with, we're assuming that gravity doesn't take any account right now. We're just going to use purely horizontal motion. Is this any different than the first one? No, because they're both under what kind of motion? Constant what?
Acceleration?
No. Constant acceleration. Why? Guys, you should be able at this point to determine this. Okay, let's go. But if you don't know how to start this, let's go to the steps. Step number 1, what's the first thing you do on the board? Draw a picture. You draw your picture. What's the second thing you do?
Facts.
Okay, and what is the first most important fact to lay out?
What kind of motion?
What kind of motion do you have? So in problem number 1, what kind of motion do you have? Vertical and
Constant acceleration.
constant acceleration. Why is it constant acceleration? Because he's falling because of what? Gravity. Gravity is pulling him down, accelerating. What is gravity's rate? Negative 10 meters per second squared. Okay? In number 2, what kind of motion does he have? Or do we have? Horizontal. And the type of motion that you have horizontally? Constant acceleration. Do you see that?
Yes.
It's just like driving a car at constant acceleration. Okay? So guys, solve these problems. Work together.
Why is it constant acceleration?
Because I've stated it that way. I've stated that he is constantly pushing that bomb at a constantly accelerating rate at 5 meters per second squared.
What's the first velocity that you 0?
This velocity of Superman initially is 0. The acceleration of Superman horizontally is 5 meters per second squared. I want to know the time it's going to take to get to the 2,000 meters and the Superman's final velocity at that point. Does that make sense? Okay, I'm going to pause. Okay, so let's work on. Let's work on problem number 1. Okay. So on problem number 1, we're going to list out our facts. We've drawn the picture. What's the first fact that we know? It's the first fact we have to. What?
The acceleration.
But we know that the first fact we want to figure out is what? That we have the type of motion which is constant acceleration. So we know that our acceleration is constant. correct?
You already stated that, so that's fine.
I'm sorry?
Nothing.
Okay. Then, what is, if we have constant acceleration, what's the equation that we can use, or our two equations that we can use?
Delta D equals 1/2 acceleration minus delta t squared.
Plus initial velocity times delta t. Don't forget that portion. Hannah, you're looking at me like you haven't seen it before. Okay. Okay.
We need like binoculars.
Yeah, you can come over here. The glare is not great.
Wait, velocity of what initial?
The initial velocity times delta t.
You just like have to listen to
So
it.
basically,
How's that?
it's a lot better.
Take a huge.
Sorry, I apologize. I tend to write small.
Well, I mean, you just write like how you would write that.
Yeah. Okay, is that cool? What's my other equation for constant acceleration?
Acceleration.
A equals change over velocity over change in time.
Yeah, change of velocity over change in time. And this is really what? How do I break delta V down? How do I break delta V down? V final minus V initial over delta time. Everyone with me? This is important because if I ask you the final velocity, you need to know that, right? And we'll do that in the next problem. Okay. So what I'm asking you is the delta time, right? What things do I know? Let's lay out my facts. Let's lay out what other things.
Distance.
Okay, so I have my distance. So I have my y initial. What other variable do I have?
Your acceleration.
Well, hold on. If I have y initial, then I have y final. What else could I possibly have?
Your acceleration.
Okay, before acceleration, give me velocity. What's this? I have what kind of velocities do I have? Variables could I get? My vy initial and my vy final, right? Then I can have my acceleration in the y, and then what else? What's my last variable? What's my last variable? Time, delta t. You guys see that?
Do we have to do all this? Or do we know that we can improve?
I would like you to do this. I would like you to lay out your facts so that I know that you know this is going to be helpful for you. You won't make a mistake if you do this, okay?
That's like really confusing me.
Why does this confuse you? This is just a checklist. This is a checklist of...
What does it mean?
Okay, so the y initial is my initial position. What's my initial position?
Y-axis.
The Superman, right?
Yeah, where is it? What's my initial position? No.
No, 80.
80 plus 80 meters. This is why I'm having you do this. It's 80 meters. Okay? Okay, what's my final y? 0. Okay? So when I do my delta distance, it's final minus initial. What does that mean about my distance? Negative 80. If you just said 80, you'd have a positive 80, and the problem is your sign is going to be off. So do it this way. Okay, so what's my initial velocity in the y?
Did you already tell us?
My initial velocity? But you can assume what's my initial velocity in the y? 0, right? It's 0 meters per second. Right? What's my final velocity in the y? Do I know it? Don't know it yet. Do I know my acceleration? What is it? Negative 10 meters per second squared. What's my time? Don't know it. Okay. The reason we're doing this, Morgan, is now you've got everything listed out clean. You know all the possible variable options, and these will never change. You have those, and you're checklisting what you have. Then you can compare your checklist to your equations and say, which equation could I use? This way you're not guessing, and you have a process in which to figure out what equation you could use. Because these equations are just relationships. These equations govern constant acceleration. They're all about the same motion. This equation, delta D, and equation A equals delta V over delta T, those equations are all about constant acceleration, the same motion. However, they relate different parts of that motion. The first equation relates the distance that I'm going to travel to the acceleration that I have, that constant acceleration, to the time that I've been traveling, and my initial velocity. The second equation relates my acceleration to my change in velocity and the time that I've been working on, or I've been traveling. So this one doesn't involve distance, and this one doesn't involve final velocity. You see the difference? So this is going to help you determine which one you want. So in this case, I'm looking for what? What am I looking for? The time it's going to take to fall. So given that, so far, looking for time, could I use either equation? Just looking at it briefly, they both involve time, right? So I have to determine, could I use both, or which one could I use, or which one could I not use? So let's go through the facts that we know. We know the initial position, we know the final position. That's our what? What's that? It's our change in distance, right? So which equation uses change in distance? The top one. Does the bottom one? No. It doesn't mean we couldn't use it, but let's see. Okay? Do I know my initial velocity? Yes, I have my initial velocity. Beautiful for both cases. Do I have my final velocity? I don't. So now this equation here, I don't have my final velocity. It's one unknown that I don't have. But I don't need final velocity for the first equation. What about acceleration? Do I have that? I do. So that's for both equations. Great. What about my delta time? I don't have my delta time, do I? Because I'm looking for it, right? But they're in both equations. So what does that mean about the bottom equation?
You don't have to.
I don't have what?
You don't have time.
Yeah.
Velocity.
Yeah, so I have two unknowns. One equation, two unknowns. Can I use the bottom equation? No. How many unknowns do I have in the first one? Just the one. Can I solve that? Yes. This is the process you go through. You follow me? You have to conceptually first up. By the way, if you don't understand what kind of motion you have, you're done. You've got to know that. You've got to be able to assess that correctly. Otherwise, you're going to be working with completely different equations. Make sense? Got to assess that. And then from there, you can start to break this down in a systematic, organized way. And that way, you will never mess up. Is that cool? Okay. So now that means I can use a top equation, right? So delta distance is really what? What does delta distance break down to? How do I break down delta distance? Final minus initial. And my distance is in the y position, so it's really y final minus y initial, right? Equals what? Finish out the equation. 1/2. Let's finish up the variables first. A in the y direction times change of time squared plus my vy initial times delta t. We're going to, yes. So now, do I have an initial velocity in the y? 0. So that goes to 0, right? So now my y final is what is my y final? Plug it in. What's my y final? What's my y final? 0. What's my y initial? 80. So it's minus that. There's my negative. Now I'm showing that I'm actually moving down in the downward direction 80 meters. Does everyone see that? If you follow this, you'll never mess up your direction sign, right? Equals 1/2 times what's my acceleration rate? Negative 10 what? Right. Negative 10 meters per second squared. Don't forget the negative sign. Because the negative sign, because if you follow this through, then the negatives will cancel out, right? If you don't, you'll end up with a square root of a negative number, okay? Times my delta t squared, because I don't have delta t. Look how easy this is. Now, I can say that my delta t is equal to the square root, okay, of negative 80 meters divided by, I'm just going to multiply the 10 and 1/2, divided by negative 5 meters per second squared. Does everyone see how I got that? Because negative 5 is 1/2 times negative 10. And then I divided that to that side, and then I did the square root piece. Everyone follow the steps I did there. Okay? So I can come back and I can say 80 divided by 5, because the negatives cancel. 80 divided by 5, square root. Look at that. Time is what? 4 seconds. So my delta time is equal to exactly 4.0 seconds. Cool? Everyone good with that? Does that make sense? I know this process is a little bit cumbersome, but if you follow it, you'll never make a mistake. Neither with your signs or what equations you're going to choose. Okay? I promise this test will be short enough that you can finish in time. I promise it will be straightforward. Okay? All right. I will be here. I promise to be here. Okay. I'm going to move on to the... Does everyone get this? Does everyone understand how this works? Okay. Your practice, you should go back and do this problem again. Maybe change some numbers. Set up a new problem for yourself. Okay? Okay. Next one. All right. Now we've got problem number 2. We've got Superman flying with the bomb, correct? Yub yub? Huh? Yeah. So Superman's moving the bomb. Hannah, wake up. Am I boring you? Am I boring you? Cannon, will you not do that, please? Keep your hands to yourself.
I didn't touch her. She's touching me.
Hey, guys. Hannah, leave him alone.
You just said you needed the walker.
Yeah, will you not do that?
You were sleeping
I wasn't sleeping.
while a teacher.
I literally went like this, and you told me to wake
Okay.
up.
Cannon, do you need to go see Mr. Gunnan?
Yes.
And tell him what?
Tell him that why you threw the marker at Hannah?
Because she was sleeping and you told her to wake up, and
Did-
so I was helping you out.
That's not
And
appropriate.
then I didn't really hit her. I hit the chair.
Have a seat. Have a
You
seat.
guys, I can, if you go to Mr. Gunn and make it so much more complicated, you can never win. We'll see if it's under your chair.
Okay.
Well,
So again, what are my steps? Shh. What are my steps, guys? What are my steps?
No, what
No. No. What are my? Draw a picture, number 1. Draw your picture. After you draw the picture, what's the next step? I may draw some things, but you may have to draw some other things yourself, right?
Question: are we gonna get counted off if we don't draw a picture? But like if we do everything else?
If there's a picture there, then I won't count off. I may ask you to draw a picture later. Okay, I might ask you to draw a picture. Okay. I won't grade on how good the picture is. Okay. I promise. Okay. Shh. What's the so laying out your facts? What's the first fact you have to lay out?
Motion.
What kind of motion do you have? Okay, you have horizontal. Oops. You have horizontal constant acceleration. Cool? Cool beans?
The coolest beans.
All right, good. Okay, so what does that mean about our equations? What equations do we have to use for constant acceleration?
Say one.
One with acceleration.
Okay, there are 2 of them. What are those 2 equations? Let's list them out. You get a note card, by the way. You get a note card.
Acceleration equals the change in velocity over the change in time.
Okay, and what's my change in velocity? Break it out.
Right now, wait, don't we not know the change yet?
No, but break it out in terms of variables. Use variables first. Don't use numbers. What's my variable?
Okay.
How do I break delta V out?
V initial is
Final.
0.
No, that's not what I said. I said, give me variables. How does delta V,
V final minus V initial over delta T.
acceleration is my delta V over delta T, right? Delta V is V final minus V initial. Do you guys see that? Delta V is just that, right? It's just V final minus V initial over delta T. It's the same thing.
T final minus T.
Yeah, it's T final minus T initial. But time is always going to be positive, so I'm leaving that complexity out of it, okay? Does that make sense? Yub yub? Yeah, be up. Okay. So what's my other equation for constant acceleration?
Change in distance.
Change in distance.
Equals half of the acceleration times
Okay. So, and what? How do I do change in distance? What's change in distance?
final distance
Minus distance initial. Distance minus distance initial. Okay, that's going to equal now what? I'm sorry, 1/2.
half of the acceleration times
Delta t squared plus what? Initial times delta t. Do you remember why this is important, guys? Do you remember why this is important? Okay.
If you start with if your initial velocity, if you start with an actual initial velocity, then it changes.
Okay. Let's consider the two scenarios. This guy right here, acceleration, distance that I cover is acceleration times my time squared times 1/2. That is just constant acceleration with an initial velocity of 0. If I look at just that portion, that means that part's 0, right? That's like I'm at a stoplight, and when the light turns green, I hit the pedal to accelerate. Correct?
Yes.
Okay. This portion together, both of them together, means I'm cruising down the highway at 50 miles an hour next to a semi. And at a certain point, I decide I want to pass the semi. So I have to accelerate from beyond my initial velocity of 50 miles an hour. Which means that I'm going to cover more ground because I'm accelerating, but because I have that initial velocity of 50 miles an hour, I'm still going to cover distance due to it as well. Do you follow me? So total, I'm going to cover more distance accelerating from an initial velocity than I would just accelerating from standstill. Yes, Carmen?
So, what would be the change in time in like a situation?
Both the same thing, same time, right? It's all about the same time. Right? It's because again, we look at our graph, our velocity versus time. Okay, it's either this or it's this, where I have an initial velocity. Right? I've got this area under the curve as my delta d, right? Versus, oops, I'm going to come back to this for a second. Versus this area under the curve, which is this guy, oops, plus this guy. You see that? The first triangle is just this guy. The second thing is the rectangle, which is this dude right here, and then the other triangle above. The triangles are the same size, but I have on top of that initial velocity I was going. Does that make sense? Okay. All right. So now let's continue to lay out our facts. So we've got the equations, we know the kind of motion that we have. What are the things that we have? Let's list out our possible variables. What are our possible variables? Okay, let's start with distance first. So my initial what? Initial distance. So x initial. What's my other one? X final, because I'm x for horizontal. You could use pink elephant initial, pink elephant final. Doesn't really matter. Okay. What's my next thing? Vx initial. Because I don't have any y right now. It's all horizontal. So Vx final, bless you. What else do I have? Two more things. Acceleration and time. So the acceleration in the x, okay, and delta time. Okay. Okay? So notice we have acceleration in the x. We've never really had acceleration in the x before, but does it matter? It's the same thing. Think about yourself, like you could say, well, I'm accelerating vertically because of gravity, or I'm accelerating horizontally because I'm in a car. And you're going, well, do the equations apply the same? Well, think of it this way. If I'm out in outer space, away from the Earth, there really is no up or down, is there? But if I were going to be going in one direction, constant acceleration, doesn't it matter? You know that it really doesn't matter what direction you're going? So that these equations work regardless of your direction, as long as the motion is the same kind of motion.
So, like, since it's not gravity, so it's not
So then you have to give us the acceleration.
You either have to be given or you calculate, right? I could tell you his final velocity is something with his initial velocity. What's his acceleration rate, right? And we'll do that in a little bit. So, okay, so our x initial, what's our x, now let's fill out the things. What's our x initial position? What's our initial x position? 0, right? What's our final position?
2000
Negative or positive? Because it's to the right, okay? If it was the other way, it would be to the left, okay? So positive.
You're like, because it's to the right. If it was the other way, it'd be to the left.
No, maybe the other way would be negative because it's to the, yeah, I know, okay, all right.
I did that, right?
2,000 meters. What's my initial velocity? What's my initial velocity? 0 meters per second, right?
We don't know our final.
What's my final velocity?
We are unaware.
Unaware, do not know. What is my horizontal acceleration?
It is +5.
Positive 5, because I'm going to the right. Okay, positive 5 meters per second squared. What's my delta time? Don't know. Okay. So now I'm asking you what's my delta time and what's my final velocity. And so how do I determine what equation I can use?
You look at what you have and what you don't have.
Okay, so what do I have? What do I don't have? Let's pick one first. Let's look at time. Look at time. Can you solve time anywhere? Where could you use time? Both? Given with what you know. Just one. Which one could you use? The bottom. Why can't you use the top?
Because you don't have the final velocity.
Final velocity. You don't have that. And you don't have time, right? So we're going to look at this guy. So we're going to say, all right. We're going to say, what's our final position? 2,000 meters is 2K meters. Minus my initial position, which is 0 meters, which equals, what's 1/2 times what's my AX? Plus 5 meters per second squared. Plus what? My initial velocity of 0 times delta t is 0. Then you can solve for times delta time squared. There you go. Okay.